On the other hand, as I say, we have a series of characteristics that suggest that they retained an ability to climb. Okay. One of the most obvious of these are limb proportions. Okay, so the proportions of the arms and legs. And here we have comparison between a human and a bonobo, a paniscus. Okay, and hopefully immediately you'll see there's some very obvious differences in terms of limb proportions. The length of the leg being 1, that's very obvious, and also the relative length of the arm. Okay, so chimpanzees typically have, compared to us, short legs and long arms. And in the figure next to it, we see the same bonobo specimen being compared with Australopithecus afarensis, with a reconstruction based on Lucy. And again, you can see that the limb proportions are very similar. Okay, so they had limb proportions that were more similar to chimpanzees than they are to ours, suggestive of a retained ability to climb. The shape of the rib cage is indicative of climbing. Orientation of the shoulder joint is indicative. They had relatively long, curved fingers and toes. Again, that comes out very clearly when you go down to Seattle and look at Lucy. She's got remarkably long and curved fingers and toes. And also, interesting evidence come out recently in terms of the organ of balance, the semicircular canals, the inner ear of the Australopithecines are much more similar to what we see in chimpanzees and gorillas than they are to what we see in humans. Okay, so we have a series of traits that suggest that these were probably animals that were what's referred to as facultative bipeds. So they walked around bipedally like us some of the time, but also were able to climb much more efficiently than we are. So this has been a sort of consensus that's been built up over the course of sort of 30 years. Early on, the Australopithecines were really sort of depicted as being sort of little humans in terms of their bipedalism. Here they are out in the savannah. This is a recent reconstruction from National Geographic, which gives this sense of them having a much more mixed mode of locomotion, including climbing. Okay, and so this sort of reflects the consensus in the field. Relative size of the teeth and jaws, again, sort of links with diet and how difficult items are to process in the diet. It's pretty clear that the Australopithecines, at least these early ones, Afarensis and Africanus, had relatively big teeth for their body size. Okay, so we're not talking about relative here, it's relative to body size. So if you look at the size this is the mandibular symphysis, this is the front of the mandible. These are the lower first and second molars. Okay, and this figures our body mass. If you were to look across this in detail, I'll sort of spare you going through these in painful detail, but basically the message is, for little animals, they had relatively big teeth. Okay, their teeth were much bigger relative to their body size than ours are. Okay, relative brain size, they basically had chimpanzee-sized brains when we compare them to body mass. So we've got chimps at the top here, common chimpanzees, cranial capacity, species average of about 410 cubic centimetres, body mass somewhere in the 31 to 39 kilogram range. Afarensis, brain size between about 400 and 500 cubic centimetres, with body mass between 29 and 45 kilograms. Africanus, similar sort of story. Okay, so these were animals that basically had chimpanzee-sized brains. Okay. And also importantly, they didn't have an extended childhood. Okay, so they basically grew up relatively rapidly. So there's been some really fantastic developments in terms of looking at the interior structure of teeth that allow us to get at the rate of development of the teeth of an individual tooth, and therefore to get at the development of the individual themselves. And the basic story here is that humans and apes differ significantly in terms of their rate of dental development, and humans are basically slower than apes. Okay? And when we look at the Australopiths, what we find is that they're basically growing their teeth fast like apes. Okay? And the inference from that, because there's a linkage between rate of tooth growth and eruption, we basically can infer from that they had a relatively fast developmental schedule. They didn't have an extended childhood like humans. Okay, so that's the early australopiths. Turning now to the later australopiths, about 2.5, we see what seems to be a bit of an adaptive radiation going on. We certainly see the appearance of some interesting anatomical characteristics. So we're now turning to this group of species here. There are several here. We've got Paranthropus aethiopicus, dates from about 2.5 to about 2.3 from a couple of sites in Kenya and Ethiopia. It's a rather wonderfully preserved cranium here, the black skull count MWT 17,000. We have Paranthropus robustus from a series of sites in South Africa, and we've got a number of very good specimens for this species, including this wonderful cranium SK48. And Paranthropus boisei, perhaps the most striking of the fossil hominins, found at a series of sites in East Africa and also down at this site of Malema in Malawi, dates to about 2.3 to 1.1 million. As I say, it's extremely sort of striking cranial morphology. Homo habilis, from a series of sites in East Africa and also a site in South Africa, Sterkfontein, dating from about 2.4 to about 1.6. And then Homo rudolfensis, a couple of sites. Cubi4 has yielded a number of specimens, and then there's this mandibular fragment from Uraha in Malawi, dates to about 2.5 to about 1.6 million. Don't have a very large number of specimens, but one of the ones we do have is this wonderfully preserved cranium, Canamir 1470. And then lastly, in terms of these species, we have Australopithecus gari, dates to about 2.5 million from this site of Buri in Ethiopia. The primary specimen is this reasonably well-preserved cranium from one site in this area, and it's been suggested that some postcranial bones, these ones here, may also belong to the species. And compared to the early Australopiths, we can see basically two sort of divergent routes being followed here. Basically, we see with the Aethiopicus, robustus, boisei, and gari, we've got a similar sort of body size and locomotor strategy as far as we can tell, but larger teeth and jaws. Okay, so there's a greater emphasis on the chewing morphology here. Brain size is basically similar to what we see in the early Australopiths, or slightly larger, and they also seem to have developed pretty quickly. Habilis, rudolfensis, similarities in terms of body size and locomotor strategy as far as we can tell. Teeth and jaw size is similar relative to body size to what we see in the early Australopiths, and then slightly larger brain size in one of these species. Quickly then, so body size, similar sort of story to the early Australopiths. They're basically chimpanzee size, both in terms of body mass and also in terms of stature. Relative size of the teeth and jaws. I'm just going to draw your attention to these guys here. These two paranthropine species, boisei and robustus, their jaws were massive, okay, particularly boisei. Okay, just look at the difference here. So we have Homo sapiens out. This is an average for modern humans. Okay, and let's just take the size of the lower M1, the lower first molar. Okay, for a modern human, the average is about 11.2 millimeters in terms of diameter. Boisei, 16.7. Okay, and this is in dramatically larger than us, and this is in something that's dramatically smaller than us. Okay, it may be difficult to actually get your head around what these figures actually mean. Just as a way of an example to illustrate this, your molar, your first molar, is about the size of a small fingernail. Okay. The teeth of boisei, the equivalent tooth of boisei, is about the size of your thumbnail. Okay. So these little individuals had huge teeth. Okay. They also had huge jaws. Okay. And it seems that they were basically adapted for chewing items that were very difficult to process. Okay, maybe nuts, maybe seeds. Okay, so there's been adaptation, natural selection has produced these basic chewing machines. The first specimen of Boisei was nicknamed Nutcracker Man for obvious reasons. Relative brain size, the only one that really sort of stands out here is Homo rudolfensis, that has a brain size of about 752 cubic centimetres in a body size of about 46 kilograms, as far as we can tell. So the rest of them are pretty similar in the same sort of ballpark as the sort of chimpanzee and the early australopiths.